Okay, so in section 6.3, we're dealing with like radicals. Like radicals have the same index and the same radicand. So for example, if we look at a real simple one here, I have a square root of 2 and then a 3 square root of 2. The radicals are the same index. The radicands are the same, both 2. Okay, so therefore I can basically break this up into a simple first grade problem. This is essentially asking me what is 1 plus 3? 4. It's 4 square root of 2. Okay, it's no different than if I had said x plus 3x. It's 4x. Doesn't matter how complex it looks. As long as the index is the same and the radicand is the same. So essentially here I have 1 minus 8. Right? Because my index is the same and the radicand is the same. This is no different than saying 1x minus 8x. 1 minus 8 is negative 7. So I have negative 7 times the cubic root of 9x squared y. Okay, so the property for this, again, like I said, is like the distributive property. It is the distributive property that gets us there. But essentially, you're saying that if my radical is the same, all I need to do then is add the numbers that are out in front, add the coefficients of those radicals. And that same thing holds true in subtraction. Okay? So let's try a couple of examples from our notes here. Off to the side, starting out with example A. Do we have like radicals? Yeah, we do. It's a square root of 5x and a square root of 5x. So essentially, if I break this down to a first grade problem, what am I asking you for?
3 minus 2.
Well, yeah, I'm asking, hey, what's 3 minus 2? The answer is 1, but I have 1 what?
5, square root 5x. So just 5x.
No, not just 5x. Square root 5x. Got to make sure to have the radical. Means something totally different. Okay? So, square root 5x, that's our answer. Looking at part B, am I able to add those together?
No.
Absolutely not. Why?
Because they have different radicands.
The radicands are different, and actually there's something else that's different.
These squares.
The terms, the like terms aren't the same, right? We have an x squared and we have an x. So, because of those two reasons, these are not like radicals. All right, how about part C?
You can't do it because the indexes aren't the same.
The indexes are now different. The radicands are fine, but now the indexes are different. So again, these are not like radicals. We cannot add them.
Man, these problems are so experimental.
Okay. All right. Now, by the way, just because we're not able to add or subtract two terms like this doesn't mean that we can't simplify them down. I know there's at least one in your homework that asks you to add some stuff together. Well, you're not able to add them together, but you are able to simplify each one down. Okay? I still want you to do that. If you can simplify each individual radical, you need to do that. Okay? But even so, then if you're not able to add them together or whatever, then we don't add them together. All right? So, let's take a look at the next part A. Are we able to do that, guy?
No.
Nope, same reason as the last one, right? Indexes are different. These are not like radicals. All right. We had 3 of those in a row. I think we got that. All right, so let's take a look then at 2 that we can work. So, taking a look at the second example B, I have 3x square root of xy plus 4x square root of xy. If I break this into a first grade problem, what am I asking you to do?
3 plus 4.
7.
I'm asking you to take 3 plus 4 because the stuff that's the same is the x square root of xy, right? That's the stuff that's the same. And so we're taking 3 plus 4, which as you said is 7. So we have 7x square root of xy. And then how about our last one?
17 minus 15.
I'm essentially asking you what is 17 minus 15. Because again, the radicals are the exact same thing. They're both fifth roots, and the radicand is 3x squared. So, 17 minus 15 is 2, 5th root of 3x squared. Okay, so taking a look at the bottom of your notes here. Sometimes when we are adding or subtracting radical expressions, we need to simplify the expressions first. For example, here, I have the square root of 12 plus the square root of 75 minus the square root of 3. Those are not like radicals, the way they're written now. Okay? So, if you remember back to last week, which was section 6.2, we were multiplying and dividing radicals, right? Multiplying and dividing radicals. In that process, we came to the conclusion that it is easier to actually multiply them together first, then simplify, right? That's kind of what we came up to. It's just, just multiply them together first, write them under the same radical, then simplify it all down. Well, with addition and subtraction, you have to do it the other way around. With addition and subtraction, you have to simplify first before you can add or subtract. And the reason for that is because we can't combine unlike radicals. Okay? There is no way for me to take square root of 12 plus the square root of 75. I can't do that, so I have to simplify them first to find out if I even can add these guys together. Okay? So let's see how that works. We have the square root of 12.
4 and 3.
So the biggest square root or perfect square that comes out of 12 is 4. So we have the square root of 4 times 3. Very good. Now square root of 75.
25 and 3.
25 times 3. And then we have minus the square root of 3. Can't do anything with that. So simplifying this down, what is the square root of 4?
2.
So I have 2 square root of 3 plus the square root of 25 is 5 square root 3 minus the square root of 3. So again, thinking back to a first grade problem, this is asking what's 2 plus 5 minus 1?
6.
6.
Square root of 3.
So let's take a look at the next one. Now this one does have cubic roots. So that means you're going to need to have your roots chart out because I doubt many people have your perfect cubes memorized. Okay, so dig out a roots chart. I'll give you guys 2 minutes to simplify down this expression. So cubic root of 250, you need to look at your roots chart. You need to look at what perfect cube goes into 250 evenly. 125. So we have the cubic root of 125 times 2. Now, here's the key thing to look at. It's kind of a hint for the rest of these. 125 is the perfect cube. It's 125 times 2. So, we need to go through and find the cubic root of 54. And I'm saying, well, wait a minute, that times 2, this is probably going to be a times 2 as well. Now, maybe it's possible that it can't be reduced, and maybe it's possible that this is as far down as I can simplify it. But if I can do this problem, if I can combine all these together, then it must be times 2, right? So what times 2 is 54? Is 27 on your perfect cubes list? Yes, it is. Okay. And then minus the cubic root of, again, something times 2 gives me 16. What? 8. And is 8 on your perfect cubes list? Yes, it is. So we can then take the cubic root of those items. So what is the cubic root of 125?
5.
So that's 5 cubic root of 2 plus cubic root of 27, 3 cubic root of 2 minus cubic root of 8,
2.
cubic root of 2. And so really what am I doing here? I'm taking 5 plus 3 minus 2 times the cubic root of 2.
6.
So again, we get 6 cubic root of 2. Out of your notes, we are now going to be multiplying binomial radical expressions. Okay? Fancy way of saying that we have binomials with radicals in them. So, binomials we dealt with back in first semester. We call them binomials because there are two terms put together, right? It's a binomial. There's two terms added together, so it's a binomial. So I'm taking this binomial times this binomial. So there was a four-letter F word that we used to multiply these guys. What is that?
FOIL.
Yes, it's FOIL. That's the four-letter F word.
And if you had Mrs. Bayer for Algebra 1, she did double distribute.
Right, and we some teachers call it double distributing. Yep. So what we're going to do is we're going to go ahead and take that first term in our first binomial, and we're going to just, basically my idea of FOIL and the double distribute, it's two different names for doing the exact same process. I take that 4 and I distribute it through the second binomial. Okay? So I end up with 20
Plus 16 square root 2.
plus 16 square root 2, exactly. Okay? Well, now I take that second term in my first binomial and I distribute that.
10 square root 2.
So I get, plus 10 square root 2 plus, now here be careful, 2 square root 2 times 4 square root 2.
8 square root 2.
8 square root 4.
Doesn't it end up being 2 anyways?
It ends up being 2, but not square root 2.
Oh, okay.
Okay, yeah, be careful here. Because this is reminiscent of last week. Last week we were multiplying radicals. And remember, when I was multiplying radicals, they had to have the same index, which of course both of these do. And if they had the same index, then I'm able to multiply the radicands. I can say I have the square root of just 2 times 2. Okay? So the square root of 2 times the square root of 2 is the square root of 4.
So it'd be 16.
So our answer, this will be 16 because what is the square root of 4?
2.
2. And so then what is 8 times 2?
16.
So this is 16. All right. So now we want to combine like terms and combine like radicals. So we always want to start with our whole numbers first. Put the radicals at the end. So we want to take 20 plus 16.
36.
Then we want to take 16 square root of 2 plus 10 square root of 2.
26 square root 2.
And that is our answer. So please take a look at example B, 3 minus square root of 7 times 5 plus the square root of 7. And please try that one on your own.